Hello everyone, my name is Hsieh, and I'm here representing our team, Team ORSOL from Purdue University. We are a diverse group with expertise in data analysis, programming, and problem solving. Before we enter into our project, let me introduce you to our team. This is our Professor Siva from Industrial Engineering. And then this is me, I'm the project manager, which is the project lead of this Team ORSOL. And then my fellow teammates, Jae, Jihyo, and Ethan. Today, we'll be walking you through our project on how economically vulnerable populations are disproportionately impacted by climate change. In this presentation, we'll begin by introducing the problem we are addressing, followed by the data we work with, our methodology for identifying high-risk counties, visualization and demonstration of our SAS dashboards, and finally, the results of conclusions drawn from our analysis. The problem we're tackling is the intersection of economic vulnerability and climate change. Essentially, climate change doesn't affect everyone equally. Vulnerable populations, those who are already facing economic hardships, are often the ones who suffer the most. This is a societal challenge because as the effects of climate change intensify, they deepen existing inequalities. So, why is this a problem? As climate change accelerates, we are seeing more frequent and severe events like floods, heat waves, and storms. These events disproportionately affect low-income communities. For example, people living in poverty often don't have the resources to relocate or rebuild after disasters. This problem affects millions of Americans, particularly those in rural and economically disadvantaged regions. It impacts their housing, job stability, and even access to healthcare. We've seen real-life examples of these impact in areas prone to heat waves, where low-income communities face high rates of heat-related illness because they don't have the ability to afford air conditioning or they don't live in the properly insulated home. Our major goal of this hackathon is to build a system that can identify the top 50 counties most at risk due to the combined effects of climate change and economic vulnerability. To do this, we had to create our own methodology that integrates data from various sources and ranks counties based on the comprehensive risk scores. And now I'll let my teammate Jae to continue with the data processing part.
We use 4 key datasets. The first is FIP National Climate Assessment, which provides projection of environmental impacts such as extreme heat, cold, and precipitation changes if global temperature increased by 3 Celsius compared to pre-industrial level. We encountered several data quality issues during the processing of this data. In particular, many smaller counties had missing data, which required data cleaning and standardization to resolve. To address these issues, we implemented code-based data cleaning, identifying missing values, replacing incorrect entries with NaN, and dropping unnecessary columns to streamline the datasets. Through these efforts, we were able to organize the 4 datasets consistently. After cleaning the data, we selected the key variables for our analysis. From the climate data, we focused on extreme heat, cold, and precipitation changes. From the economic vulnerability data, we selected poverty rates, unemployment rates, and workforce engagement. These variables allowed us to analyze how exposed each county is to the climate risk and how economically vulnerable they are. The goal of this analysis is to identify the regions most vulnerable to climate change. Here is the list of key variables we selected.
Thank you, Jay. Now we will go in depth with our methodology. At first, we consider a straightforward approach, basically ranking the counties based on raw values of the dataset. While this might seem like a logical approach that could work well, it doesn't account for the complexity of how different factors interact. For example, high unemployment rate of a county does not necessarily mean that county has a After we figured that the first approach wouldn't work, we came up with an alternative approach which could really show us how strong the relationships are among different variables with unemployment rate of each state. We began by running a correlation analysis on SAS between the climate and social vulnerability variables, hoping to see some. After those approaches, we came up with our final solution, and it was to create a risk factor scoring system. We categorized our variables into 4 main directions: heat extremes, cold extremes, precipitation extremes, and social vulnerability based on workforce engagement. The main directions were determined. Before applying our Python algorithm for the scoring system, we began by pre-processing the dataset to ensure the values of each factors were appropriate. Our first step was to address the missing data. During our initial analysis, we identified a significant number of missing values that needed attention. For numerical columns, after pre-processing the dataset, we were ready to begin building our scoring system. We started by assigning weights to each factor, with more impactful or important factors receiving higher weights. Our initial calculation for the score involved multiplying the raw value of each factor by its weight and then scaling the result.
Thank you, Jihyo. Now I will explain the visualization and demonstrate the dashboard on SAS Visual Analytics. This dashboard highlights two key climate risk factors related to rising temperature: the increase in summer days with higher average temperature and the growing number of days where the minimum temperature exceeds 70 Fahrenheit. These metrics provide a clear view of how heat driven by climate change is impacting our environment and help us understand the associated risk. To address cold temperature risk, this dashboard shows the number of days with temperature below 0 and 32 Fahrenheit. A heat map displays regions with fewer extreme cold days, while a bar chart compares selective counties on the day below these thresholds, illustrating how warming trends are reducing cold extremes. This dashboard also visualized global warming's impact on precipitation patterns. The heat map depicts total annual precipitation change under a 3 Celsius warming scenario, while the bar chart compares the counties by overall precipitation and extreme rainfall days, offering insight into how warming influences weather events. This dashboard assesses economic and social vulnerabilities. A heat map shows county-level unemployment rates, and a comparative chart displays employment, unemployment, and poverty percentage across counties. These visuals offer insight into regional economic stability and vulnerability. Lastly, this dashboard integrates climate change and socioeconomic vulnerability factors into a comprehensive risk score systems. It assigns weight to variables such as temperature extremes, precipitation patterns, and socioeconomic metrics like unemployment and poverty rates. The heat map visualizes composite risk scores across counties, while the detailed list in the line chart presents the top 50 counties with the highest risk score. This approach highlights the area most vulnerable to the combined effects of climate and social factors, aiding in prioritizing interventions.
Thanks for Ethan for bringing us this clear demonstration. And now let me continue to finalize our results and conclusions. In our analysis, we identified the top 50 most vulnerable counties based on our own risk scoring system. Here are some examples of the counties that ranked high. Example county in Arkansas ranked the top due to the extreme heat projections combined with high poverty rates, making its population particularly vulnerable. Another example county in West Virginia was flagged for both economic instability and high flu risk, compounding the challenges that the residents face. These examples demonstrate the intersections of climate risks and social vulnerability that our methodology highlights. While our own risk scoring system works really well for identifying vulnerable counties, there's always room for improvements. In future iterations, we could expand our analysis to include additional variables such as race and age to account for specific population vulnerabilities. We also see the need to factor in transportation access, which can significantly affect a community's abilities to evacuate or recover from disasters. Finally, health infrastructure is critical. Counties with limited access to hospitals are at great risk during extreme weather events. Our analysis provides clear policy recommendations for addressing these vulnerabilities. First, policymakers should consider investing in climate-resilient infrastructure, especially in counties prone to flooding, heat waves, and other extreme weathers. Additionally, targeted economic support programs can help these communities build resilience by providing job opportunities and financial relief. Lastly, strengthening healthcare system and disaster response capacity is critical for managing the health impact for climate change, especially in rural and unserved areas. These will be it for our SAS Hackathon video presentation. Thank you all for listening.